Good day everyone, we are going to start with casting 2. This will be lecture session number 9 for MGC, and it will be lecture session number 3 for manufacturing section of the module. Today we will be starting with centrifugal casting method, and this will be building up from the previous casting method that we dealt with in the previous manufacturing lecture session, which was die casting. So centrifugal casting method actually originates from the fact that we use centrifugal force to perform casting procedures. We spoke about slash casting previously, where we indicated that you have a ball that you want to manufacture, but you don't care about the internal dimensions of that ball or the hollow space. You don't care about the hollow space of that internal section, but you are only concerned about the outside shape. So you put that molten metal into the mold, and then you rotate your mold around to form a ball, and then when you're done you will take out your molten metal that will be on the core, and then you will have a hollow spaced component. For centrifugal casting we use it also to get hollow dimensions, but we are also concerned about the internal dimension. So you'll think of pipes. If we start talking about centrifugal casting, some of the pipes are manufactured from centrifugal casting. So on a pipe you'll have an outside diameter which is of your concern, and also your inside diameter which is your concern. And how you can make sure that you can get these diameters accurate to the dimensions that you need, you will have to know the density of your molten metal. You'll also need to know the volume which you must pour, and then you start with the rotating procedure. For centrifugal casting you have the mold, which I can now start indicating with my mouse over here, and you have a driver roller which will be responsible to drive the mold. So let's just recap that. You will have a drive roller, and then you will have the mold. Inside the mold, that is where you're going to pour your molten metal, and then you have a free roller, but this roller is just there to control and balance your mold. So think about it, you can have this drive roller in the center, maybe on this side. Look at this picture side view. You can have that driver roller attached directly there like your gear system, and then on the other side of that molding procedure you can have your pouring point. Remember that point should be in the center, because when you have a component rotating, the innermost point on the zero radius dimension, that point we can assume is not moving. So you will have a hole there, and then you will pour your molten metal through that hole, and then you can position this whole machine such a way that you will have this molten metal flowing to the point where you need the molten metal to fill, which will be determined by the casting dimension that you are looking for. You will now see that we will be starting with calculations, and as I said, the centrifugal casting actually arises from the fact that we'll be using centrifugal force, which we define by this equation here. That force, which will be centrifugal force in this case, is equals to mv squared over r, and the mv squared over r will mean this will be your mass, and then this will be your velocity. And note that this is a linear velocity, we will discuss this, and then this will be your r. So your r will be radius to a point where you are actually focusing your direction at. So we can now start thinking, think of this approach here. You have your rope, and then at the end of the rope you attach a mass, and then on the other side you start rotating that mass using the rope. You will be the center, and that mass will be at some distance r. So that is the distance r we are talking about here. And then the gravitational force will be your weight, which is mass times gravitational acceleration. This you will always be given. This you might, because it's a universal constant, this will be given to you, and the mass will be provided, or you'll have to determine that from somehow on your calculation, maybe using density, maybe using volume given. So that, just think about it from that point of view. And then you have another factor here, which is called a G factor. A G factor is a man-made factor, but it was derived as a method which can help us to gauge as to where do we put our force, centrifugal force, and where do we put our weight. What weight should we impose on our system, and what force, centrifugal force, must our system attain. Remember, centrifugal force is determined using velocity, which we will still define as to how will you get that velocity of a rotational component. The G factor depends on a lot of things. So the G factor that I said we will be using will be only applicable in this module. So between 60 and 80. And note that the G factor does not have a unit, because it's a force over force factor, and your velocity of this mass will be determined using this equation here. This is a linear velocity, and you have to get it from a rotational velocity. Your rotational velocity will be n, and this will be your linear velocity, and n is given as a revolutions per minute or revolutions per time. Looking at the time that you will be using, or you will be given, you need to know how to transpose this equation here, or how to transform this equation here, so that it can actually yield the units that we are looking for. But when we look at our force and we see that our G factor is equals to centrifugal force over weight, when we define it here, we can have this force defined like this. And for this particular equation, it will be very important that you actually understand how we transpose it from F over here, GF is equals to F over W, and how we get it over here. But it's just substitution of equations into this main equation here to end up here. In the case that you are required to solve for n, you also go further, and then you take your G onto the other side. You now apply your square root to cancel out the square that you're looking at, so that you can have this equation here. So at some point you will be asked to determine the revolutions which the casting was performed at. At some point you'll be asked to determine the diameter, given all the other aspects, or somewhere you will be given aspects where you first need to determine a certain factor, then you go further to determine a next factor to be able to solve another factor. So it will not always be a direct question given to you that you can just simply calculate, substitute your numbers into these equations to solve your problem. And you can have this G factor written like this, or written like this, or written like this, depending on what you are dealing with. But we will get to see from you practicing that actually when you are given these factors, maybe let's say you're given time in terms of seconds, how do you derive this equation? Or when you are given time in terms of minutes, how do you derive this equation? But the aim will just be for you to be able to transpose or transform rather GF from here, transform it into this equation. From here you should be able to get this equation to calculate the rotational speed using all the factors that you will be given. So you can use this method to manufacture tubes which you can manufacture in the horizontal direction or in the vertical direction. When you manufacture in the vertical direction, you need to look at this equation to calculate your revolutions per second or your rotational speed. The reason for this, and you can start seeing that we have now two R values. The one will be the R value at the top, and the other one will be R value at the bottom. This is when you have a vertical tube that you need to manufacture, and you will never have these two equal to each other practically and analytically. When you're looking at this, we can see that if we have these two together, this value here becomes 0, and this factor here of the equation becomes infinite. Practically, if you have a vertical molten fluid poured into some hollow tube which is vertically or rotated vertical, you will always have that fluid trying to go down because of gravity, and because fluid deform, you will always have a lot at the bottom than you will have at the top. And the other method that will be called semi-centrifugal will be, centrifugal casting will speak about semi-centrifugal casting. The semi-centrifugal casting, instead of having a hollow part manufactured, you are going to have a solid part, but it follows the same procedure. And then the last one will be centrifuge casting. This particular method over here will have small components being casted, but these components, actually think of this as a cup, and around this center line over here, when you look at from the top, you have several cups, maybe let's say 6 or 8 cups around here. So you will have a cup at the end, a cup at the end in the opposite direction. And the reason why you want to have them more or less in the opposite direction is just that you want to balance out your cups. So if one is at 90 degrees, the other one should be at 180, and if one is at let's say this will be your 0, 90, the other one should be at 270, 0, 180, the other one should be on 180. So you'll have one here, one here, one here, one here, so you'll have 4. But ideally it's just to balance it out. If you can calculate it in such a way that you can balance it, you can get any number of small components that you can actually cast using this method. Quality, so casting qualities. So this will actually just we are now talking about problems that you can encounter when you do casting, any different type of casting. You can have number A there, misrun. You want to cast this whole component, but you don't fill it up all the way to the end. The second one over here, you have cold shut. There you can see what we have there, a cold shut. You have a core there, but somewhere here you have a problem. You can have number C there, a different type of cold shut. You still have holes, but you are not looking for holes. And then you can have number D, shrinkage. When you start shrinking your remember what I said in the previous lecture, that your molten metal, when it's hot, it expands a little or a lot, and when you start cooling it down, it will shrink. Maybe when you shrink it, it will open some cavities, so that will be another issue you have. Number E, microporosity, just like this one here, but you have microporosity, so you don't have your molten metal all around your solid part. You have spaces there. You can start thinking of this one chocolate that I think we are all familiar with, and it has holes inside when you break it. So that would be an example of microporosity, but I just thought of that example quickly. And you will have here hot tearing. This happens mostly when you have sharp corners. You will have sharp corners, and this is related to that shrinkage cavity there. So you will have this, and it's formed by more or less the same phenomena during cooling or during the manufacturing process. Okay, you have this was just in general. So now we have some casting defects that are common. You have blow, and I think for this particular one we try to describe as to what can happen during sand casting. You might have this because you have space there, and the air did not escape because you did not have vents. Pinholes because of sand. You can think of sand grains, and sand wash. Your mold collapsed during the casting, so it was supposed to look like this, but now you don't have anything there. You have sand wash, it just collapsed. D, over there we have scraps. Also you have sand that collapsed, and then on top it was covered by molten metal. Penetrations, collapsed sand, and then you have penetrations of that. All these defects you can start fixing with some method. I can just think of grinding this off to have your part now back straight. And then you have a shifted drag or cope. If you have these two shifted, you will not have an alignment. so you will have that defect there. Core has shifted upwards. Your core, remember with your core you need to do the calculation to determine the density and the weight and the positioning so that you don't have it shifting. Some case it will shift, and then you have mold crack. If you develop a crack in your mold, metal will go there, and that will be a defect. You have several inspection methods that you can use for this particular manufacturing procedure. Visual inspection is the first one. Visual inspection is when you look at something to check if there's anything wrong with it. We have seen over the history that this method is not the most accurate or the most reliable, because it depends on your eyes, and your eyes depends on a lot of things that are happening with you that day. If maybe you had a session where you were not okay, you might miss some of the defects. When you are happy, you might miss some of the defects, because maybe it's Friday or something like that, you are in a hurry to get home, and then you're just passing things and you don't pick other other dimensions. You have dimensional measurements. You can take a ruler and just check as a method of inspection. You have metallurgical, physical, and other testing methods that will check your quality of the product. Pressure testing will be one of them. Pressure testing is a process where we are testing, mostly you find it in pressurized vessels. You want to pressure test your vessels before you deploy them into operation. So you'll see that you'll take your pressure vessel and then expose it to pressure and see if it doesn't leak. If it doesn't leak, then you're good. There are no leaks. Radiography methods. This is a method where you use radiography to detect any cracks on the surfaces. Magnetic particle test. This is where you use magnetic particles to test the cracks. Most of this you use fluorescent penetrants. These are visual also inspection, but now you use some colorant to check if you have cracks that you cannot detect with other methods, or somewhere you don't want to have radiography around your component, or somewhere you don't want to have magnetic, then you can opt for color. Ultrasonic testing, we use ultrasonic to detect the cracks or any misproportions of dimensions on our products. Radiography, you can also think of that method that they use in hospitals to just check if your bones are fractured or something like that. So we are more or less aligned there. We apply the same principle in engineering. Repairs, welding, grinding, machining, cutting, but welding you can add material with welding, and then you can also remove by grinding. You can remove, this is just typical, but you can achieve addition of material using different methods. Today we have 3D printing, which is actually just additive manufacturing. You manufacture by adding, and then grinding you manufacture by removing. You can have machining. We will cover all this in the future sessions. So grinding, let me maybe just go here and show that how we can solve some of this by grinding. Let's say we have this, we can weld this cavity here, and then we have now a good product. There was another defect here. This defect here, we can grind it off, or this one here, the crack, we can grind this so that we have perfect dimensions. Okay, the metal that we used, the metals that we use for casting will include ferrous metals. You'll have the names are there, and then those are limiting temperatures, still limiting temperatures. And then you also have non-ferrous casting alloys. You'll have aluminium, you'll have manganese, and they all go with different properties, and they are all used for different applications. Copper alloys will also be part of that. Tin, a lot of metals you can use them in the casting procedures. But here we are starting to show you some of the components, material properties that will guide your selection of the metal. So just think of that. Some components you need them to be weak, some you need them to be strong. And remember, by weak and strong in engineering we have other topics that we cover, which also make us focus on exactly what we are looking for. So by weak, I might mean that this thing is hard when you impose force on it. By strong, I might mean that this material doesn't break when you impose a load mechanical load on it. Otherwise, I can mean this material does not break when you impose heat on it. So those are type of material properties that you also need to be aware of, but you'll get to learn them as you continue with your degree. You will get to learn those with your degree. When you design a casting procedure, you need to have a simple design that can be achieved using simple procedures. Considerations on the design: your geometries should be simple. Corners must be avoided at all costs because you don't want to have sharp corners. They're either going to break with the molten metal, or you are going to have difficulties removing those from you removing your part out of those corners. If you have permanent molds, I'm just thinking. Sectional thickness should also be uniform. You need draft so that you can be able to pull out your component. So if you have something like this, draft will be, if you just pull it out in this direction, it will be able to slide out. But imagine if this was straight, it will create a vacuum when you start pulling it out on the other side, because it will still be attached to the side. But immediately when you move this one out, let's say this was what was your mold. When you move this mold off, air occupies this space, and then you will be able to remove it. This is just fillets and rounds. Have fillets and rounds other than corners. In this module, I think you are going to be introduced to fillets of radius 3. Will be fillets and rounds. This will just be for you to avoid having sharp corners, as we discussed in the previous slides, which are considerations that you need to put when you have your mold or casting procedure. Casting design: the material thickness. You must also just read the circular web with adjoining section is preferred. Okay, that is for strength, of course, of that particular part of casting. This will also allow you for cooling. This will allow cooling. Okay. Speed up solidification. Solidification is the cooling that I was just talking about. So having a hole there will be important. Avoid having something like this, because then you don't have a cooling on this corner here. On this will be your part, so you won't have a nice cooling there. Okay. You also learn that when you have, depending on what material properties are you looking for, controlling your cooling is very critical. If you cool something very slow or cool it very quick, it might affect your material properties. If you cool something very fast or very slow, it might affect your material properties, but you will get to learn about that during the course of your degree. Okay, draft angle. Look at that angle, it's always required. Look at the radius we were talking about, it's always required. So think of that. Forging. Forging is another method which is close to casting, but it's not really casting. You heat up your material for this particular one to high temperatures, then form them by pressing on them. So you actually, so think of this. The best method that we will know, the best method that we will know and which we actually probably have been close to, if you were at some point playing with fire and then you heat up plastic, you know just before it becomes liquid it will soften up, and then when it's soft you can form it in a different shape type of thing. So that is with metal, you heat it up to a very high temperature. Before it can melt, you now form it by pressing on it. So it can be by pressing or pushing. So that will say that process is called forging. And then these are all the factors. You can have open die or closed die processes. You use pressure from the die. Die will be the component that you used. This will be your die. This will be your material. You forming this now. Okay, let's go further. Forging, there is the procedure just outlined for you. Look over here. You start with this, you start pushing, you ultimately get this shape here. That is what you're looking for. You had a material which was heated up. Okay, there's the procedure. Have and avoid having sharp corners. You will then have good products. If you don't have sharp corners, somewhere with sharp corners, you're going to have tearing. Instead of having your material flowing into the shape, it will tear into the shape. Forging continued. There you are. There you are. These are all the methods that you can deploy. Look at this one here. These are crankshafts. So you can also apply this on your crankshafts. Draft angle is very critical. Always have a draft when you do casting to avoid high friction, which will end up with tear. And forging will be the last thing that we have to deal with as far as casting methods are concerned. With forging, we will stop here, and that will be the last thing we do with casting. And the next section you can check in your daily timetable what will be in lecture number 4 for manufacturing. But we are continuing with these methods, and we will see the next method. I think they involve machines which we use for manufacturing. Thank you very much. And for this particular section, consultation hour for this week's work, that will be consultation hour for lecture number 3. We will be dealing in details with that formula that we saw in the beginning. It will be advisable for those of you who do not understand that to prepare that and have questions on that. We will be dealing with that. Thank you very much. We will meet at the session, consultation session. We will meet at the consultation session.